Three recommended books would be DJ Amit, Statistical Physics, then it is the Bioline, that's Thermal Physics, and another recommended is Schroeder, which also has, I think, the same title. Between these three, almost everything we talk about will be taken care of. For the thermodynamics part, I would recommend that you have a look at Zemansky, because the number of examples and so on are far more there than in Amit. So between these, I mean, everything that we talk about in this course would be contained in primarily Amit and Zemansky, with some consultation of Bioline and Schroeder, you would go through very well. So that's that. So as I said, it's going to be about ideal gases. And if we go back to the beginning of the 19th century, two things were known: that PV is equal, the equation of state is NKT. That was known thanks to Boyle, Charles, and Avogadro. So that the pressure, volume, and temperature of a gas, and not ideal gas, it was, they just considered gases. There was no such thing as ideal gas, which is, as the theorists came into play, the idealization started occurring, as it always does. And that is when the word ideal gas came up, primarily because that this equation of state needed corrections towards the end of the 19th century, and therefore you had to differentiate between real gases and ideal gases. Ideal gases go with this equation of state. Real gases have corrections. So anyway, that's we are concerned with, we will be concerned entirely with this through this semester. And it was the contribution of Boyle, Charles, and Avogadro which gave you this picture. Question was, or will be for us, which is a sort of, I mean, essentially trying to put everything that happened through the 19th century in perspective, that how do I get a theoretical handle on PV equal to NKT? What? So primary question for us, what is involved if one tries to derive PV ideal gas law? Now, what's derive? So what's the meaning of, what could be the meaning of the word derive? The word derive in this case means that there were two things, where, there was just one thing which one knew very well at the beginning of the 1800s, and that is Newton's law. So Newton's law was the known tool for physicists and chemists who wanted to look at this. And the question of getting a theoretical basis for PV equal to nkt means that can I start with Newton's law for these collection of n molecules running around in a box of volume V. This is the number of molecules enclosed in a box of volume V. Goodness gracious, this room is like a furnace. There's some kind of circulation of bloody, put on some fans somewhere. Seems to work. Huh? Okay, I'll just trying to figure out if this room can be cooled in some way or other. Oh, yeah, right. Okay. Yeah, all right. Let's see. So you have these n molecules, and I want to use Newton's law in order to get a handle on how this is going to emerge. So the first order of business is getting familiar with Newton's law. So I'm sure you know, but what is supposed to be known about it. But let's get on the same wavelength on this in this matter. So I'll start with a question that Newton's law have a potential V of x, which is 1/4 lambda x to the power 4. So Newton's law is mx double dot, that is the your mass times acceleration. And if this is the force potential per particle, then this is let's say per particle per unit mass, that is. So per unit mass, then it is m times dv dx is the force, which is this, and so x double dot is equal to minus lambda x cubed. And I want a solution, and I give you x at t equal to 0. So t equal to 0, x0, let's say, is equal to 1. So I've placed the particle at x equal to 1 at time t equal to 0, and am asking whether you can give me a solution for this Newton's law business, x double dot problem, of mass in a per unit mass, this potential is this. So it is a quartic potential instead of your standard quadratic. And so that is just to make things a little different. And so this is your equation of motion. And the question is, if I give you the initial condition, can you give me a solution? So that's the question. So how would you react?
So I think yes.
Pardon?
So at x equal to 0, we can the value of x equal to 0 is 1. Then we can find the value of x double dot 0 at and then we can form the equation. We can basically find the value of lambda and then put the
lambda is given to you.
Okay.
So lambda is given. Lambda is no lambda. Let's say is equal to 1.
Sir, minus 1/4 into x power 4 plus 1. If lambda is equal to 1.
Pardon? Lambda equal to 1, let's say.
Yes, so then minus 1/4 times x power 4 and plus 1.
Sorry, what did you say? I didn't quite. So your equation has now become x double dot is equal to just minus x cubed. And I have given you x of 0. So at t equal to 0, x is equal to 1. And I'm asking for the solution. And what did you say?
So x, the function is minus 1/4 times x power 4 plus 1. X power 4 minus x power 4 divided by 4 plus 1. So,
minus x by 4 minus x to the, so you are saying x of t is equal to minus
x to the power 4.
X by 4, x to the power 4.
Yes, sir.
But you have to find x of t. How can there be a
Yes, sir, it is x dash t. X dot t means dx dt, I think. He is saying about the dx dt part.
Sorry. All right. What you are, this is xt is equal to x dot over 4. You are saying minus x dot over 4. That correct? No, or are you saying x dot is equal to something?
Yes, sir, I am saying that x dot equal to something means x dot equal to.
X dot, you are saying x dot is equal to something. So x dot is equal to what? All right, I get it. You are saying x dot is something. So x dot equal to?
So it will be something x equals to minus t square by 2 plus ct plus 1.
Minus t square
by 2. X dot. No, sir. Only x. X dot no. X equal to.
X equal to minus t square
by 2 plus some constant into t
plus some c times t
plus 1. Yes.
All right. So if I take now, can this be a solution of this? Left hand side is x double dot, which is equal to minus 1. And the right hand side is the cube of this. So the equation is not satisfied.
Sir, I am saying that x dot x dot equals to root over of minus x to the power 4 by 2 plus c.
X dot is equal to
Minus
huh?
minus x to the power 4 by 2
X to the power 4 by 2
plus c whole to the power half.
plus t whole to the power half by 2.
Plus, yes sir, plus c, a constant, not t.
Plus what did you say?
C sir, any constant.
E.
Any constant sir. C.
Any constant. So
Yes,
all
sir,
right,
yes.
some C.
Yes sir.
Yeah. Now this is x dot is equal to some constant minus x4 over 2 by c. But actually this statement is correct. But this is not, I want to know what is x as a function of t. This statement is correct. So whether it is correct regarding the 2, I'm not so sure. I would have got a 4, but let's not quarrel about that. I'll accept your, I would have written a 4. And I would, but instead of, I would have written x to the power 4 over 4. But since there is a arbitrary constant, I'm not quarreling. But that does not give me a solution. I want to know x as a function of t. So what are you now? This is the correct first step, but this is the first step. I now want you to tell me, can you get me x as a function of t? So the question is, I'm going to let me there are 2 bothers me. So let me make it a 4 and sorry, or 2. Yeah. So fine. 2 is all right. I see what why I would have. Yeah, the 2 is. Yeah. So the 2 is all right. Sorry. The thing is, you have got x dot is equal to c minus x4 divided by 2 to the power half. I will not ask right now how you got it, but since you got it is correct and it's correct. We'll talk about that later. In a minute. But now my question to you is that, can you tell me x of t from here?
Sir, we can get x dot as a function of t by again differentiating the x double dot equation, that is Newton's equation.
Pardon?
Sir, we can differentiate Newton's equation once again, that is the one where it's written x double dot is equal to minus x cube.
Differentiate, that will make it a third derivative and life will be very complicated. Differentiate, no,
yeah.
Don't.
Sir, but sir, if we take a triple derivative, then we will recognize the equation because it will be a harmonic oscillator equation. From there, we can get x dot.
That's rubbish. It can't be a harmonic oscillator. What is correct is what the answer has been given till now, that x double dot equal to minus x cubed implies that x dot is equal to this, because I multiply both sides by x double dot. So this is minus x cubed times x dot. And this, if I have a 2 and I put a 2 over here, then I can recognize this as ddt of x squared, that is ddt of x dot squared. So ddt of x dot squared is 2x dot times this. And over here, I have to recognize a ddt, and that is minus half ddt of x to the power 4. So ddt of x to the power 4 is 4x cubed x dot. So now you have ddt of this, ddt of x dot squared plus half x to the power 4 is equal to 0. So x dot square plus half x4 is a constant, and that exactly is what I was told by one of you. So that is absolutely correct. So, and that is the first step over here. And now try to address my question that I have given you x of 0 is equal to 1. Can you give me a solution? Solution means that if I write t equal to 5, I will be able to figure out what x of 5 is. That means that is what is meant by a solution. That I will give you an initial condition, and you will give me once you have you will give me x at every subsequent time. So so this is serious business actually. It is after this step. Do all of you understand this step? Are all of you comfortable with this step? That yes, if I give you x double dot equal to minus x cube, then the first thing you will do is carry out this procedure and tell me that x dot is some constant c minus x4 over 2 to the power half. Or very good. So now you have to integrate once more. And all right, what will that integration? I don't want you to give me an answer in terms of trigonometric or hyperbolic or whatever functions the answer is going to come out in. I want you to concentrate on that if I do imagine that I have done this integral and obtained a solution, what will this solution contain?
So it will contain another arbitrary constant, which we
very good. It will contain another integration constant. So you integrate, and you are going to get some x of t, which will have various things. And among those various things, there will be a c and there will be a d. And how in the world are you going to get them?
We can't get it because we have got only one initial condition.
Yes, sir. We
So we need at least 2 at x0 and x dot 0 at least.
Absolutely right. So there is what what I have set over here for you is completely incomplete. You cannot give me a solution. This problem posed by me over here is rubbish unless I tell you what x dot at time t equal to 0 is. You cannot, even if you were very good at integrating and finding integrals, you would not be able to find the solution. That is the primary issue. So It is a second order differential equation. A second order differential equation needs two initial conditions. So this is the first thing that has to be sort of become a part of your system, that motion, when it is a dynamics, and you can't give me that standard rubbish which is dealt out, that you can give t equal to 0 give me x, and at t equal to 5 give me the value of x, and I will give you the whole. Technically, yes, absolute rubbish in practice. Nobody gives you a x at 5, or you have an initial condition. The whole meaning of dynamics, which you have to understand, is that dynamics is prescribed at t equal to 0, and you are required with that information to crunch out numbers at future times. There are two kinds of differential equations in this world. One is the initial value differential equations, which class of initial value, which are these over here, what you are seeing over here, Newton's law. It's an initial value differential equation. Then there is the other class, which is called a boundary value differential equation, where you are given information at two different points. Wholly different approach, wholly different concept. And this is the first fundamental thing that you have to understand about the differential equations in physics. And it's not a mathematically wrong statement. It is what mathematicians probably won't tell you, but there are only two different classes of these: initial value problems and boundary value problems. For those of you who would have to will take physics as your calling in life, better get started with this, become comfortable with this notion that there are initial value problems and there are boundary value problems. If it is dynamics, it's an initial value problem. I will give you the weather conditions, the pressure, this, humidity, this and that today, and would like to know it tomorrow. I don't, and after giving you the dynamics, I don't give you the pressure today and the temperature tomorrow and ask for the dynamics. So you have to understand why it is stupid to do that sort of thing. So one doesn't do that. One does initial value conditions, and that there are classifies it very clearly: initial value problems and boundary value problems. So this is an initial value problem. So that's lesson number 1. So all right, initial value problems. So what you are dealing with is Newton's law, and Newton's law is an initial value problem. Now, all right, so what about it? I wouldn't like to, if it is an initial value problem, I would like it to become absolutely transparent to me that it is an initial value problem. So I ask the question, when can I get by with only one constant? That is, if I have a first order differential equation. If I asked you to solve dx dt is equal to f of x, then it would only be one initial condition on x, and you would be able to give me a solution. But if it is what Newton's law is all about, that d2 dx squared, d2x dt squared is equal to some f of x, then I need to have two initial conditions. And this I would like to clarify by writing Newton's law as two first order differential equations. Dx dt is equal to something, and then equal to some function sorry, equal to some p, and then dp dt is equal to f of x. So that is how what you do is you introduce two independent variables, x and p, which is what dynamics is all about. Dynamics is prescribed only by prescribing the position and the velocity of a particle. That is practical life, and that is the only life. You need to know, if you need to know the state of a particle, you need to know where it is and what velocity or momentum does it have. So the state of a particle in Newtonian physics is determined by x and p, and the dynamics of x and p, Newton says, is dx dt is equal to p, dp dt is equal to f of x. And now I give you x0 and p0, and you are through. There is no question of not being able to solve, or the worst case scenario is that you can't give me an analytic answer, but you can march through with anything of your choice, whether it is Rungekutta or more the favored thing, which is this Adam Bashford or whatever, but Rungekutta, which is standard, which is straightforward. It's a calculational tool, and you use a numerical tool. You can use it. If I give you this, whatever f of x I give you, you can always give me. If this is given, you have xt and p of t. So that is lesson number 1, which is very important for trying to get the dynamics visualized, because that's what the whole idea of this kinetic theory business is. I have got this gas. There are n molecules running around. So if I have these n molecules running around, and out of that I have to calculate things like pressure and total energy and things like that, I have to know about what the dynamics of these particles are, so that you know how many collisions it is going to have with the walls of the container, how much energy transfer is going to take place, and so on and so forth. So over a course of time, and then sort of do an average to find out what the pressure was, and so on and so forth. So the dynamics is all important. If you don't know the dynamics, you cannot track the particles, and the way you track the dynamics is this. But now this is the beginning of things getting out of control. One particle, any f of x that I give you, you would be able to give me a solution. Two particles, all right, number 1, that you would be able to give me a solution. So what does that mean? That means I can, on this plane of the board, draw the solution. So if this is x and this is p, and at t equal to 0, this is the point which I have given you, then if you are lucky and you can get the curve, then you will get the curve. And if you are not lucky, the f of x is nasty, then you can at least get points at various different times, and you can get the trajectory of the particle. So you can visualize it. It's all very nice to put it up on the xp plane, and you can see that the trajectory of the particle is just some curve which comes out of this solution in the which can be drawn in the XP plane. So very good. So that, but now, I mean, maybe the particle is moving not along a line. This means that the particle is moving along a line, but maybe the particle is not moving along a line. The particle is probably moving in a plane. So if it is a particle moving in a plane, so this was a particle moving in a line, along a line, and now I need to talk about a particle moving on a plane. So plane means that I must have X and Y. So the coordinate of the particle is specified by X and Y, and its momentum is specified by Px and Py. And now you can't draw it anymore. I mean, you can't, that is on this board. X and Px was all right. So here was my X and here was my Px. No, all right, I did have XY, PX, PY. So X and PX right here. And now it is Y and PY. So what am I going to do? If it was only Y, then you can still say, that's all right. I just put out an axis over here. So there is a third axis. I have the perpendicular to the plane of the board, and I can imagine that I have this, and this is Y. But now where is PY? So PY you can't draw, because all our experience is limited to the three-dimensional world. So when I ask you, if I ask you that, can you tell me what I did over here, what I did over here, can you do the analog of that over here? Then your equations of motion are dx dt equal to px, dpx dt is some function which can be of, let's say, the potential depends only on coordinates. That need not be always true, for example, if magnetic fields are there, but let's not get into that complication at least. Py and then dpy dt is equal to g of x and y. So there are four. So there are four, and in principle, everything is all right. I have to give you initially x0, y0, px0, py0, and you will churn out for me xt, yt, pxt, and pyt. No problem at all. I mean, worse comes to worse, tougher computation. But that's about all. It's right now my interest is only a matter of principle. Yeah, yes, go ahead.
Sir, there are some people waiting in the meeting room. They can't enter. Can you let them in?
Yeah. Very good. So xt, yt, pxt,
Sir,
yeah.
sir, can you please explain how the dpx dt or for the matter dpy dt will depend on the other coordinate too? Like it's a function of both x and y.
Take a potential which is x squared plus y squared whole square. So let's take a two-dimensional problem where the potential is a function of xy is x squared by 2 plus y squared by 2 plus 1/4 x squared plus y squared whole square. Right? So that is my potential x and y. And now when you want to write py dot, you have to write minus del p del y, and minus del p del y from over here will bring in a term which is x squared y. And similarly, when you write dppx dot, you will have, what is? This is one of my g's, f's or g's. So this is fxy is, this is v del x, and py dot is minus del del y. So it has one term which is minus x squared y by 2. Px dot similarly has a term which is minus xy squared by 2. Yeah. Right? By 2, or the 2 is not there. It is 2, which is x squared y squared, and then I take a derivative with respect to y. I get rid of the 2. Right? Got it? Yeah. So y,
That's
I mean, yeah. All right. So, so the structure and the point we are spending because these are elementary issues of mechanics which you need to know. Otherwise, life just gets stuck. So xy px py, and now y is here, but where in the world is py? And this is where all that you need is imagination. So what you need is imagination, and you imagine that there is a fourth axis somewhere over here, perpendicular to the other three. So that is in a space which is in your mind and not actually in front of you. So here is the most, and now this is what I want you to get absolutely clear in your mind. This is no longer the world that you observe. The dynamics with these two particles is not happening in a three-dimensional world. It is happening in a four-dimensional world where I can actually imagine the dynamics as a single trajectory. Do you get the point? That if I imagine a world where the axes are x, y, px and py, then the dynamics is a curve, is some curve in that space of x, y, px, py. Just as it was a curve in this, on this board over here in the xpx plane. So if I put a px subscript over here to make it a, so one-dimensional motion. It is going to be, I mean, your, and I could visualize it, single particle motion in one dimension. I could visualize it as a trajectory in the xp plane. Single particle motion on a real physical plane, which is the xy plane, cannot be visualized in our usual way of visualizing. It is in a space which has 4 axes, x, y, px, py, and the state is a point in that 4-dimensional space. And just like this chap over here, in this 4-dimensional space, the trajectory is a curve. See if you get it. I mean, otherwise, I mean, this is important to understand the qualitative dynamics. We have to deal with n particles in a 3-dimensional space. So life is difficult, but it is difficult only in a transient fashion. This picturing has to, you have to become comfortable with this picturing. Once you are, it's something that you have not seen before, but once you have seen it, once it sinks in, it's obvious. I'm trying to picture a state. I mean, we are going to talk about n particles, which is n is 10 to the power 20. So I have to, and I'm going to be interested. This is kinetic theory, thermal, where all the particles have to be kept track of. So you just try to see how 2 or 3 particles one has to keep track of, and what one does to keep track of 2 or 3 particles, and the rest you can imagine very quickly. So I'm starting with 1 particle where life is simplest, but 1 particle in 1 dimension, easy to track. 2 dimensions, immediately you have to use your imagination in trying to picture on what sort of a curve it is going to move. The imagination is in trying to visualize that it is still moving on a curve. But this curve is not in the space that you are comfortable with, but it is a space which exists in your mind. It is a 4-dimensional space which the axes are all still orthogonal to each other, just like x, y, z were orthogonal to each other. X, px, y, py are all orthogonal to each other. And if I want in this space, it requires 4 numbers to specify a state, and this dynamics is the evolution of this state in time, which is a curve. Do you have the picture?
Yes, sir.
Huh. Do you get?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah. All of you, more or less, are you more or less comfortable with what is going on? I mean, this is, I mean, you are seeing it for the first time, so therefore it can be, once it sinks in with a 2D, with this 4, talking about 6 and 10 and 20,000 makes no difference. So this is important to visualize, yeah, that I have these, I have a system with where I have to talk about a particle dynamics in a plane, and I'm trying to visualize the particle dynamics in a plane, which I want to visualize as a curve. This curve is a curve, not in the sense in which we are used to curves, but it is a curve in a xy pxpy space.
So is it like this, that for n number of particles, means for a single particle we require in a 2-dimensional we require 4 coordinates, in 3-dimensional we require 6 coordinates.
Yes,
Then
right.
fixed number of dimensionals are required for n particles.
Yeah, right.
Okay, sir.
Yeah. So now this was one particle in different dimensions, but suppose now I have 2 particles in 1 dimension. It is the same issue. So 2 particles in 1 dimension, so on a line, this is something I really don't want to, the particles on a line is a bit of a problem, one line, because particles can't, they can't go through each other. So in practice, it is a bad thing to talk about. But the thing is that if I ignore the physics of it and just talk about the maths, then I have a 1 dimension d equal to 1, things on a line, but there are 2 particles, and there is x1 and x2, and there will be px1, and there is going to be px2, and once again it will be this structure, that the potential, your potential is a function of x1 and x2. And you are going to have dx1 dxt is equal to px1, dy1 dyt is py1, and then dpx1 dt is some function of x1, sorry. dpx1 is some function of x1, x2, and dpx2 dt is some function of gx1, x2. So similar structure, 2 particles in 1 dimension, 1 particle in 2 dimensions. So same 4-dimensional world. So 4-dimensional world, and once again, if I want to look at the trajectory of these of this system, in what I would need the x1 px1, and then I have cleanly x2, but then some imaginary px2, some imaginary px2 over here, which is in my imagination, but it is this x2 px2 x1 px1 giving me a 4-dimensional space. So single particle in 1 dimension, the trajectory lies in a standard 2-dimensional surface. 2 particles in 1 dimension, I'm already at a loss, and because the space in which the trajectory is a curve is a 4-dimensional space, and similarly, 1 particle in 2 dimensions is going to be this. So if I have n particles in d dimensions, d is 1, 2, or 3. So d is just 1, 2, and 3. D is real. I mean, in the sense that it's either moving on a line or moving in a plane or moving in the three-dimensional world. So D can only be 1, 2, 3. But if you have n particles and D dimensions, then the space that you have to look, the dynamics, each particle in a given dimension requires two coordinates. So therefore, x and a p in a dimension. So the space dimension is 2nd. So if I want to visualize n particles, so moving in a d-dimensional space, and want to think of it as a single trajectory evolving in time, then the spatial dynamics, according to Newton's law, would be seen as a curve in a space whose dimension is 2 times n times d. So if it is n equal to 1 and d equal to 1, then it is d equal to 2, the thing we started out with. But if it is d equal to 1 and n equal to 2, then you have this picture over here. And if it is d equal to 2 and n equal to 1, then you have this picture over here. Same 4. So either with n equal to 1, d equal to 2, or with d equal to 2 and n equal to 2 and d equal to 1. So this picture or that picture, in general, it is 2 coming from the fact that there is a x and a px. That's the 2, n, which is the number of particles, and d, which is the number of spatial dimensions, which can be 1, 2, or 3. So if I want to visualize the dynamics of the Newtonian dynamics of this ideal gas, so if I want to visualize the Newtonian dynamics of an ideal gas, then the point is that I imagine so you want to visualize, this is all in your mind, Newtonian dynamics of n particles in d-dimensional space, then you need to talk about a space with these many axes. And the state of the system of n particles, how is it prescribed? By r vector and p vector for each one of these particles. So for the ith particle, ri vector, pi vector, and I is equal to 1 to n. And so state of the is in this 2n dimensional point space, the state is a point. So state is a point in this 2nd this 2n d-dimensional space. So a space with 2n times d axis. So you imagine, just like you imagine the 4 over here, now you just keep on adding the axis in your mind, and eventually for n particles moving in let's say 3-dimensional space, which is So would make it 6. So you imagine that there are 6 n-axis, and in that 6 n-dimensional space, your particle, the state at any instant is a point, and the evolution is a curve in that huge dimensional space. So the visualization, coming back, I mean, what have we, why talk about this? Because we want to talk about things which are general, and that is necessary. I mean, we want to talk about we have to talk about n particles, and these n particles are moving around, colliding with each other, colliding with the wall. So their dynamics is what I have to track. But in how do I track it? So in principle, my tracking system is that I draw these space with 2 nd axis and take one point, which is the initial condition, and see how it evolves with time. So this is the meaning of Newtonian dynamics. Newtonian dynamics means that you are given an initial condition for, if you are interested in one particle, then for one particle. If you are interested in 10 particles, then for all 10 particles. An initial condition involves the coordinate and the momentum. So given that, tracking the evolution is just tracking all these momenta and coordinates developing in time, and the easy representation is through a point, and therefore you want to talk about this large dimensional space where the state is always a point and the points connect to give you a curve.
So,
Yes.
isn't the fact that we need 2 nd axis for plotting out the dynamics or to denote the state of the system, depending on another interesting fact that these dynamics of given maybe one particle, if it's a two particle system, is also dependent on the position in this case of the other particle, as well as the dynamics of like one dimension of the same particle is also dependent on the position of the part of another dimension of the same particle, um, because the function is having contributions from both both the particles in this case with two particles x1 and x2, or for in the case of two dimensions.
Yes, I mean, didn't wholly get it, but let me try, and you can interrupt me if that is not. Once I have prescribed for you prescribing the potential, prescribing the V means that I have prescribed all the interactions between the different particles. That is, if I'm talking about 3 particles and they are all mutually attracting each other gravitationally, let's say, then I give you a potential which is like 1 over R12, 1 over R13, and 1 over R23. So I have given you all the start with, I have given the potential is always going to be a sum over 1 over R12 plus 1 over R13 and 1 over R23. And thereafter, I mean, you start with P square, P1 square, which is a vector. So P1 square vector plus P2 square, give or take the 2m. P1 square plus P2 square plus P3 square. And then you have the energy, potential energy, which is VR12, VR23, VR13. Now, once I have given you this system, you can write down the what is R12, what is R1 dot, R2 dot, R3 dot, P1 dot, P2 dot, P3 dot. So your and the it is R1, R2, R3, three particles, R1, R2, R3 dots, and P1, P2, P3 dots. So you have, now you evolve. It is at every stage of the evolution, the R1, 2, R2, 3, R1, 3 are updated. And you have to, I mean, imagine, so the potential that I have prescribed for you is actually going to take care of every new situation that can come. There is no other situation, that is, I cannot change the potential during the, if the potential does not change during the time of evolution, then you have a completely prescribed system. See the point? I mean, were you, I mean, I thought that I was interpreting your question as you were worried about it starts out as something and somewhere along the line it starts seeing something different. If I have a large number, if I have multiple particles with interaction. What I'm saying is that, no, that won't happen because I have given you all the interactions to begin with. Nothing else can be generated at a later time.
Yes, my doubt was that actually, if we take some arbitrary like cases for x and y and px and py, I thought like for all those cases, how can we like determinately say that it will always be two indications because axis, because if the potential that is prescribed maybe doesn't allow for or doesn't have scope for interaction in between the particles, maybe we will not have contribution in momentum in one particular axis from another dimension.
No, but I mean, that has to be prescribed, whatever you prescribe it right at the beginning. I mean, right now, I mean, I'm keeping life, I'm not talking about, but I could have potentials which also depend on the velocities, but right now to keep it is all potentials depending on coordinates, and I have told you what the potentials are, and if I don't have a momentum dependence in the potential, regardless, I mean, the potential is determined entirely by, right?
Yes, sir.
And if there are, I mean, like, as I said, magnetic fields, charged particles in a magnetic field, life would be different. I mean, but I would have to prescribe the dynamics correctly with the potential, I mean, these velocity dependent potentials thrown in, so that the effect which you are talking about, I imagine that this momentum getting in the way in of the forces, that would have to be already introduced in the system at the very beginning, through, I mean, these velocity dependent potentials. Yeah.
Okay, sir. Yeah.
All right, just a sec. How am I doing on time? All right. So it is this. So what I am after is that you have to visualize these particles in as a moving trajectory in a large dimensional space. So at least, I mean, that's fine. I mean, you say that all that can be done in principle, and I can know the trajectory. So then what? So the next statement that I'm going to make is that you will not know the trajectory. So we are going to next. So here is all, I mean, everything about the principle of working with Newton's law and given initial conditions, finding the trajectory. Everything is correct, but inside this description lie phenomena where you can be caught off guard. I mean, it is all a part, I mean, it is within the system. It is not that there is any violation of this. So these things which we have said right now is the only way of doing dynamics, non-relativistic dynamics, that I should have mentioned. It's entirely Newton's law, non-relativistic, non-classical dynamics. And I have not shown talked about potential which depend on velocities, but that can be taken care of with very simple. You'll be when you do particle in a magnetic field, charged particle in a magnetic field in the mechanics course, you will see those things come out clearly. But,
So,
yeah.
Sir, didn't you mention a bit before, like we are plotting the dynamics of the system with respect to time. So and we are plotting even we determined even the everything with respect to time. We took the derivative of the position as well as the momentum. So wouldn't we need another I mean, this question could be trivial, I don't know, but wouldn't we need another axis for time in that case?
No, no. I mean, you don't see, if you had a time axis, then just imagine that I have a time axis, then life becomes very the curves will no longer. I mean, then you would have what you would have to draw is all the x's and px's. Just take one dimensional problem, that x dot is equal to p, p dot is equal to some minus omega square x. And now I know that at every time, I know the solution. X is a cos omega t, and v is a sine. If x is a sine omega t, then v, this p, which is x dot, is omega a cos omega t. Now you plot it as in a function, as a xy. So in the xy space, if you plot this trajectory, xy meaning x and velocity. So x and velocity, or x and momentum space, the trajectory is an ellipse, right? Because I mean, it is going to be x equal to a sine omega t, and y is omega times a cos omega t. So x square over a square plus y square over omega square a square is equal to 1. So in xy space, this whole thing is a check. So what are you doing? It means that at all, you start with a time t and you go on doing finding x and y, which is x and velocity, and you draw the curve, it's an ellipse. But now if I try to draw this on a three-dimensional x and y and t, what would it be? As it would now become a whole complicated issue, because at a given value of t, so at a given value of t, which would be t equal to constant, would be a surface. So at so t equal to on this three-dimensional where t is your t is no longer t is evolving independently, and at a given t you have this x and y is x is something or y is something. So you plot at that given t the values of x and y, and then you go some other t and you have some different x and y. You will see a scatter of points, but you would not be able to pick out the, if you bring time into it and plot it, life, all that I'm trying to say is the ellipse that you had in the xy plane is no longer easy to decipher. Get it? I mean,
that means we are already considering the motion is some kind of periodic, means that particular instead of x there will be a fixed value of px, or means some pxy, or there will be some fixed value of py, like that.
I mean, it is, you know, the dynamics, what the given at any initial condition, you know that from the xpx plot, you know that given any initial value of x and px, I know exactly where, I just give me that curve and I'll be able to tell you the solution. If I were to plot this as x, y, and t, I would have a third dimension, I would complicate the drawing without giving me any new insight, right? I mean, you would be plotting x equal to k, a cos omega, a sin omega t, and y equal to independently, you would have to plot a cos omega t, and in the t direction you would, at every t you would have to plot x and y, and you would get some kind of a surface or other, but not, I mean, from that you would not be able to you would be able to at the end of the day, but not as easily as you see on this, that it is a xy. I mean, looking at, you have essentially got rid on the xy plane, you have got rid of time. You are looking at all time in one curve. That's what I'm saying. That's the advantage.
Sir,
So that means, suppose there is a harmonic motion, then if there is no external force, it will be some kind of ellipse in a xpx space.
Yeah.
But if some external force is applied, means some retarding force, then it will gradually fall down to zero. Means x,
right.
y.
Yes, right.
Okay, sir.
Yeah,
Yes,
absolutely. It will spiral into the center. Right? I mean, if I have a damping, if it's a damped spring, then in the px plot, you would see that instead of closing, it would get slowly coming in as a spiral and eventually asymptotically reaching the zero value origin. Yeah, that's what will happen. Sure.
Sir.
Huh?
So can we say like because x and px in this case of one-dimensional motion and one particle system will also contain the state information at every point will also contain. I mean, we can find the time from that too. I mean, that contains the time information if we consider that we started from time t equal to 0.
Yeah,
So
sure.
we don't necessarily need to have another axis.
You don't, I mean, all the information is actually contained in those curves in the trajectory that you are being shown in a XP plane. You actually have all the information because every point on that trajectory corresponds to a particular time, right?
Yes, sir.
Sir, can I say something?
Yeah,
It is
sure.
like that. Means suppose we get a PA as a function of t and x as a function of t. We
Yeah.
have two things, and we can also modify it as a t as a function of x, and ultimately we can get a p as a function of x, and which we are getting in a phase space. Is it like that?
Yeah. Right.
Okay.
I mean, you are eliminating t. You have
Yes.
x as a function of t, p as a function of t, and you are essentially eliminating t to write a function of x and y.
Yes, the parameter, the t parameter I am eliminating from.
Yeah. Yeah. All right. So very good. So I will stop over here because the next thing that I want to talk about that this dynamics can get out of hand. So that's going to be a completely new issue for you. So we will carry on with that on Thursday. The thing is, any queries that you can have, the mail to send it to is so that's the communicating forum, that any query that you can have, anything which bothers you, you can always send and I'll try to respond as quickly as possible.
Hello, sir. Hello, sir.